All right. So Veena has started recording. All right. So let's just. Great. Great. So we have lost 15 minutes of our session. So let's try to make use of the rest of the time. All right. So so we had discussed the thing about Flume so far. So let's discuss SQOOP. Okay, so SQOOP we had talked earlier about. SQOOP is basically an open source tool to extract data from a structured data source into Hadoop for further processing. You can also move data from database as in usual MySQL to HBase. Okay, usual SQLDB to okay to HBase. All right, and you can export data back from SQL database from data to SQL. So you can also do the back and forth between the SQL to the HBase. Okay. Did we talk about it already? I think we already talked about SQOOP, isn't it? Uh, all right. Is everybody able to hear me? We were talking about SQOOP. So I think have we talked about SQOOP already? I think we have, right? Yeah. SQOOP has been done already. So SQOOP has been done, Flume has been done. So time was for OOZIE. Okay. Yes. Thank you, Naveen. Thank you, Sushant, to correct me. Yeah, SQOOP is already done because I was getting that feeling that I had done it. All right, great. Now, so we were talking about OOZIE, and what exactly is OOZIE? It's a workflow scheduling system to manage Apache Hadoop jobs. Workflow jobs are basically directed acyclic graph of actions. We will talk about what is directed acyclic graph, and it basically provides you coordinator which which can run the job as well at a certain period of time or at a certain schedule or at at so coordinator can kick in the jobs periodically as well. So OOZIE has two components. Okay, Mm, one is called coordinator and other is called the workflow. Okay, so workflow basically means that you can create a graph or a batch of jobs which are depending on each other, and you can run those jobs. Either you can run or you can ask coordinator to run them periodically or later point of time based on either either time or based on the data. You can also define that when data is available in this folder, run the jobs. Okay, so that is the role of a coordinator. So coordinator can make things work based on certain frequency or data availability. Is integrated with the rest of the Hadoop stack, and OOZIE is also scalable, reliable, and extensible system. That as we have told you that the everything we will talk about in this session is all about reliable, scalable, and extensible and distributed. So it is distributed, the OOZIE is distributed because when we give the job to OOZIE, it will run on any of the node in the cluster. This is an important bit of information that whatever we ask OOZIE to run, it will run it in the network. All right. So all right. So we have let's define something called directed acyclic graph. What exactly is directed acyclic graph? Directed acyclic graphs are everywhere. Every day we use directed acyclic graph to subconsciously to solve our problem. For example, let me try to draw something. All right, let me try to draw something like getting ready for office. Okay. So getting ready for office means you uh, need to take you need to take you need to wear shoes. Okay, and of course you need to wear the the pair of pants, and you need to wear shirts shirt and and tie, right? And of course socks. All right. Now, when you now let's think about the order in which we can wear things. We wear these uh, clothes. Okay. So you cannot wear a tie before wearing the shirt. Okay. So to wear the shirt, let me draw the diagram opposite way. To wear the shirt, you need to wear the tie first. Oh, sorry, not tie first. To wear the tie, you need to wear the shirt, right? Now, let me just make these diagram look like this. Now, to wear the shirt, we need to also take bath. Okay, we need to take bath. And yeah, right? So to get ready to the office, we need to wear shirt, we need to tie, we need to wear shoes, and etc. Now, we can we wear the pants before shirts? Not generally, but let's try to make that graph. So we wear first shirt and then pants so that we can tuck it in. All right. Now, if you see that the wearing pants depends on shirt, wearing tie depends on shirt, wearing shirt depends on taking bath, and then only after we wear the pants, we wear the socks. Okay, so it's a hard dependency. Okay, we cannot we so wearing shoes is a hard dependency on the socks. Okay, because you don't. Now you see that to get ready for the office, you need to do these things, and effectively, the first thing which you need to do is we need to we need to take bath. That is the first thing we do. Okay, that is the first thing we do. Now, after taking bath, we will. So this is sort of first thing we will do, and then we will wear the shirt, and then either we will wear the pants or we will wear the tie. Okay, this order between tie and pants is totally different. We can also do things like shirt, pant, socks. Okay, and six. Now you can see that, and then get ready for office. So what you saw just now, this is called topological sorting. Okay, so this is a directed acyclic graph. Okay, this is a directed acyclic graph, and in this directed acyclic graph, you cannot have circles. Okay, first you cannot have circles. That's why it is called, and it is directed. It's a graph, as in things are connected. Things look connected to each other. So, but it's not something like we can do tie or shirt at any point of time. You have to wear shirt before tie. Therefore, it's a directed. So these directions represents order in which doing things. Okay, and So this is and given such a graph, preparing the list of order of things is called topological sorting. Name is bigger, but these are totally commonsensical things. Like with most of the computing, the ideas are very rudimentary and simple. It's a word which is really big and difficult. Take a case of, say, pigeonhole principle. It's a discrete mathematical term. It just says that if there are three pigeons and uh, if there are four pigeons, they cannot fit in three pigeonholes. So most of this is actually a big common sense, right? So just that the terms are different, but when the concept become complex, it's become little difficult to combine these simple terms to make form a complex term. So for example here, given this kind of graph, preparing the order of things might become very difficult. Okay, there are set of algorithms which, although you can come up with your own algorithm really well, but it takes some time given a big complex graph to figure out the topological sorting. Okay, all right. So Randhir, this is called topological sorting. Are you able to hear me clearly? Is the idea of to this idea of directed acyclic graph. This is called DAG. So, so DAGs are everywhere in computing. If you are from a background of if you have written a build script, for example, Apache Ant, and you have used, say, what do you call, say, Make, or you have used project planning. In project planning, when you define the dependencies between tasks, you are basically creating a DAG that finish this work before this, after this, before this, after this, and so on. So you're basically creating a dependency between the terms, between the tasks, and it will give you the project plan accordingly. Okay? All right. All right. So this is called directed acyclic graph. So you can see here also I've tried to give you an example, and you can see that although it looks like cyclic, right? So can somebody give me the topological sorting of the graph that you see in the diagram? Anyone? The topological sorting in this graph? When we say topological sorting, it means the order in which we want to do the things. So if we have to do 5, what is it that we have to get done? In what order? 5, 7. So yes. Anyone? If we have to get 5 done, we need to get 11 done. And then we have to get 2. Yeah. So no. You have to first tell me the thing which has to be done first, not the thing which has to be done last. So to do 5, what are the things? Let's say your objective of the day is to get 5 finished. So 5 depends on 11, depends on 10, 11 also depends on 9, and 11 also depends on 2. Okay, 2 has to be done first, 11, 5. That's what you're saying. What about 9? You don't need 9 and 10, Bina. Okay, Sridhar is saying 5 and 7 are starting point. So 5 and 7 will be done at last. All right. So Randhir is saying the ordering for 5 would be, let me see, others have also. Yes, Veena, you're right. Just a little more details. Okay. 3, 2, 7, and 5 are also starting point. Yes. So yes, Randhir, you are right. For 5, the topological sorting may be 2, 9, 10, 11, and then 5. Yes. Okay. So, all right. So here, so if you have to do things in the topological sorting, so to get 5 done, you need two. First, you'll do 2, let's say, and then you'll do 9, then you will do 10, and then you will do 11, and so on. Okay, basically we are given these kind of graph, we are trying to say what is the order of things to do. So for we could do 2, 11, 9, 10. Sorry, I'm very sorry. Yes, that's right. That was Randhir's answer. Good. For 5, we can do this. Now, for 3. Now, after this, if we have done this, we can also, for let's say I want to get 3 done. Okay. For 3, what will be my order of doing things? I would like to do 9 first. Okay. I like to do 8 afterwards. I like to do 10 and then 3. For 7, what are the order of things I would like to do? 7 depends on 11 depends on 9 and 7 depends on 8. So let's do 9 first because 8 and 11 both are depending on that. 8 and 11 and then 7. Although you can see that the for 7 the alternated uh, so this is also correct. This is also correct, right? This is also absolutely correct. Now, for say what was that? Not 2, 7, 3, and 5. 7, 3, and 5 are the basically the ones on which nobody else is depending. So is that correct? Or even for 5, you could have different order of things. You could do 9, 2, and then 10, and then 11, and then 5. Correct? Good? Everybody okay with this? Yes, that's correct, Randhir. Thank you. All right. So these are the order of things. Given in a physical, you know, in a real scenario, probably everybody will be able to do it very easily and quickly. Okay, because these are something which we do every day. So this was a quick overview of something called directed acyclic graph. You will see a lot of things as you go forward, as you observe in computing, that a lot of things are basically directed acyclic graphs. Okay, all right. So now in case of workflow, when we talk about workflow, it's a workflow is made up of many actions. Okay, so here there is an action called word count. Let me create today's notes. Okay, let me create today's notes and Okay. Vina's question is, can you please give us a scenario like this in big data? Let me try to give you a good scenario. I think it's a good time now. Good that you reminded me. All right. All right. So discard this. I'll start with something else. Okay. All right. Now, where is my questions window? All right. So let's take a case of generating recommendations. Okay. So in case of generating recommendations, what you do is first you need data, right? And what data, let's say your objective is to generate recommendation for an e-commerce company. All right. So, and you're generating recommendation based on the user's behavior. So what you do is you first load the data. Now this loading of data could be done in Flume. Okay, so you used Flume to load the data. That's your starting point. Now everything else would depend on loading the data. Okay, now you might be parallelly loading the data using SQOOP. So your workflow will involve, okay, your workflow will involve SQOOP. All right, so we have SQOOP. Good. Now, using Flume, you can load the data, and then using SQOOP, also you might be loading some data. Once you have done the loading of the data, here you might clean up this data using, say, Pig. While you could clean up the data, this other data using Hive. Now, this will depend on loading from Flume. This will depend on loading from SQOOP. As in, here we are loading unstructured data. Here we are loading SQOOP. So at the end of both of this, like we will show you, let's say we are joining the two data sets. Okay. So what is it that we are doing? Let's talk about an e-commerce company, which is loading the Apache web server logs. So load logs. Okay. Here using SQOOP, we are load load dictionary. Okay. We are loading the dictionary. All right. Is that clear? So basically we load the logs, we load some data from a structured store, and then we combine them together and form something like, say, something like clean data in the form of user ID, comma, product ID, comma, the rating. Okay. So we formed clearly this kind of storage. All right. We after combining the two data set, we form the clean data. Now we feed this data to say Mahat. Now Mahat will take this as input, okay, and give you the it will give you the it'll give you the using Mahat we generate recommendations. Okay. Now once recommendations are done, you might want to send it back using SQOOP. Uh, you might want to send recommendation to web server. Okay. Now why it's so big? Can't we change it or something like? Okay. Now using SQOOP, we might be doing this. Okay. All right. Now, so you can see that basically the idea is to generate the recommendation which need to be sent to the web server, right? In the web server, which is showing your website, you will show these recommendations saying this user ID. If that user ID comes in, you will query the database and display his recommendations. Okay, and for that, so for transferring these recommendations to database, you need to first generate the recommendations. And to generate recommendation, you will use a tool like Mahat. But Mahat wants the data to be formatted in a clean way. User ID, product ID, and rating. Now, to do this kind of magic, to do this kind of preparation of this three-column data, you might require the Apache logs and you might require some dictionary. Apache logs are in the format of which user visited which page at what time. That is that is something which comes from Apache logs. Now, using that, you could figure out that which user is visiting which page again and again. And based on this dictionary, we could convert a page into a product ID, right? And then do all kinds of magic and prepare this uh, nice data in the form of comma separated values, where first column is user ID, second column is product ID, third column is rating. Okay? So is the case study clear? No? Great, great. All right. So we are able to create. So basically, let me just save it somewhere. Maybe I'll just duplicate the slide. All right. So from here, I'll remove it. From here, I'll remove the other two items and we'll move it to the main workflow. It looks a little ugly, but yeah, but it gives an idea. All right, so that was our quick example, and we have already done this part. We have already done this part. We've already done this part. We already done how to clean the data, how to clean data using. Uh, we have done these two things. We have done Pig and Hive. We we will, I mean, this is also done cleaning data here after you got the data. You could do it either in pig/hive, okay, by using joining data, using joins or saying in whatever way you want, okay. So, and after that, you could use Mahat. We will do this, and we have already done this part. Okay, we will do it after OOZIE, this part. Okay, good. Now that was a quick example of how to use OOZIE in order to in order to create complex workflows. So this diagram, though it looks very simple, there may be other complications. So Sridhar's question is, Mahat is OLAP? No, Mahat is basically a program which runs and is basically a machine learning library which does complex things and which runs complex algorithms. It has a set of algorithms like for recommendations, for cluster, everything. Okay. Now, so we will talk about Mahat, we will talk about in a minute. All right. So that was this was a workflow for workflow for generating recommendations. Okay. All right. So now let's break it down into individual items. So everything is an action. This is an action. This is an action. This is an action. This is an action. And this is an action. This is an action. So as per OOZIE, all of these items are action. Individual action looks like something this. You can see here, I've increased the font here. You can see here that, is the font visible to you? Okay. Is the font visible to you here? Great. Now let's have a look at what exactly this looks really complex. So workflow in OOZIE, just like Apache Ant, or there were a few more examples where workflow is defined in kind of XML. So if you've used BPEL, business process, BPEL, there's something BPEL, business process, E for something, and then language, or BPEM, business process management. Those all have similar kind of graph, similar kind of XML. Now, so if you look at this clearly, what exactly is this? It's a XML that represents a workflow that contains only a single action. This is a single action. If I delete everything inside it, that will make it a little more clear. Okay, so uh, so this is a single action from here to here. It has got a starting point. It has got ending point. Okay, so in this workflow, you need to define an action, and here we have an action called MapReduce. Okay, so we also do in the workflow, what's the name of the workflow, what's the XML namespace, so that it can give you suggestions that this is wrong, this is right. Okay, and it has to have a starting point. Starting point as in, and we have to tell which action to get into. Just like in our graph, we said, let's create the topological mapping for 5. Let's create the topological mapping for 3. Similarly, one of those points will be your starting point. And based on that, it will get into the rest of the graph. Now, here, start to word count. We are saying the starting point is our this action. Okay, now this action might depend on something, as well as this action might tell that once this action finishes, go somewhere else. Right here it says on OK, go to end, and on error, go to kill. Okay, what is kill? Kill means it prints this message, and end means this. Okay, so and the actual action is this MapReduce. You can see that the actual action is this MapReduce. It says that it's a MapReduce, a kind of the predefined tag, where we have to tell what is the name, the IP address or the URL of job tracker, who is the name node, and what are the various properties of various values. Okay, MapRed, Mapper, org, these things, and whatnot. So here you can see that if you have whatever is your stub mapper class, you have to mention here, here, and stub reducer. You remember our discussion on MapReduce, and so on. So all the things, all the information required by this particular action has to be defined inside it. So there will be all kinds of actions, right? And so this is a example of a single action. Now what if you have the full graph where there is a dependency? How will it look like? Let's go to that. Okay, let's take a look at the complex graph. So OOZIE let you create the forks. Forks as in you can split the flow into the two things, meaning the second and third, you can start second and third as soon as first finishes, and you can define a join where a join will wait until both second and third are done. And once it is done, we can send it to end or we can send it to error. To error, we generally define at every point, whether first, second, third, or final. Anywhere if the error occurs, it will directly jump to kill. Okay, so let's have a look at quickly how does our workflow looks like. So that was our one example of workflow. This is another example of workflow. It's a workflow application. Here we are saying action is this, then fork, then action, and so on. So you can define the dependency. Here we are saying when the first job finishes, send it to fork. And when the for in the fork, we are going to start second and third job. And what does the second job do? It starts MapReduce. Third job, it starts MapReduce. I'm just taking only the MapReduce case. It could have been Pig, it could have been Hive, it could have been something else. Okay, so and once both of these finish, they go to join, right? And in the join, it says they send it to final job. And in the final, this is the MapReduce. This is some other action. It could be Pig, Hive, Mahout, or whatever. And once that finishes, it goes to end. It says OK to end. All right. So this way, you could cleanly define your own. Okay. Now, Naveen's question here is this fork our word? This one. Okay. Yes. No, sorry. The fork as a term. This is our word. Okay, we could say my fork here, my fork. Okay, or while this one, this is an action, a special kind of action. Okay, this is a special kind of action which basically creates two graphs. Okay, so this one is ours, while this one is a predefined keyword. Okay, predefined tag. Good question. All right, sounds good to you? Or we could have something in a simple manner. All right. So there could be multiple forks in the single XML. All right. So that was our OOZIE description. Now let's try to understand how does a typical program in case of Hadoop looks like. And since most of the programs are executed through OOZIE, we will have to understand how does the layout of the project looks like. So in the example which we gave, okay, let's say here we are say cleaning the data. We are, where was my diagram? Is it done? Yeah, I think it's done. So let's say here at this point, we have some MapReduce as well. So we will have one big script, one Hive script, one Java program for MapReduce, or maybe we have defined custom Pig UDF or Hive UDF, right? So we'll have a few things. One is individual programs script, we'll have Java program, and we will have workflow which defines individual actions, right? So the layout, let's try to understand the typical project layout. Okay, let's try to understand that typical project layout. So if you do not have that, you can copy this to your home folder. Okay, and then you can extract it, and then you can basically upload it into your Hadoop file system. So this command will extract. Okay, this is a copy command. It is copying from this location to your home folder. Okay, and this is a extract command, which is which is extracting this particular file into your home folder, and it will create a folder called examples, and then using examples you are copying it to the your HDFS, and locally we modify job.properties under MapReduce, for example, if you want to run MapReduce. Okay, so I'll try to show you the layout. And so who defines the workflow in an organization? The person who is responsible for overall delivery. Somebody like an engineering manager who is basically managing, I mean, dev, what do you call? We call them SDM or maybe senior engineer. So who has an overview of what all is going on? In generally in a bigger project, you have different kind of people working on different parts of things. Say for example, people who are working in Pig are the people who are having a data analytics background, or people who are working in Hive would be generally people who are from databases background, and the people who are working on, they say, this portion where you are doing the recommendations, they might be data scientists. And then people who are working on this part may be the people who have understanding of their web server. All right. So basically, there could be different set of people involved in a single project, and generally, the person who has a complete overview of what's going on in project defines this workflow. And it all varies from team to team and organization to organization. So generally, in some organization where the product manager is very hands-on person, product manager takes care of writing this kind of a workflow. While in some organizations, it could be the SDM, it could be the senior engineer, or I mean, we call it SD2 or SD3 at Amazon. So they take care of writing this kind of a workflow because they generally have a overall picture clear as in what's going on and who is doing all of this. Okay. And good. Now moving on, let's try to first log in into my account. So Susan's question is there a build script for Hadoop? OOZIE looks a bit familiar to and that's right. That's right. So you will see the build script in a minute. I'll show you. So today's, all right. Now let's go to this one. I hope it's working. Yeah, it has come. All right. Now let's try to go to Hue. Hue is at what location? I think it is at d.cloudxlab. I don't know what is it busy in. All right. All right. I'm already logged in. Good. I did not need this actually. So you can also log in, click on Hue, and then Okay. Ganpati and everybody, are you able to hear me now? Great, great. Actually, this GoToMeeting again uh, stopped, and that is why. So, Veena, I hope your recording is going on because every time it exits like this, my recording gets corrupted. Good that we have a backup. All right. Yes, great. Now, I was trying to show you something. I was trying to show you how does, I have already done these steps. I have already copied these examples and then I've extracted it and then I've uploaded these examples onto Hadoop, okay, onto the HDFS. And till here, let's have a look. All right. So where is my file browser? Let's go to file browser. Okay, so here there is a folder called examples. Now in these examples, you generally have three folders. One is SRC. SRC contains your Java code. Okay, SRC contains your Java code. You can see that. All right, and this the name of the project you're keeping here is examples. Now under apps, also, you will have generally inside SRC, you will have a build script in Ant or some other tool which you use, say Maven or something else. So in here, you will have that Java build script. Okay, so first what will you do is as soon as you want to build your project, you will compile it and create the jar and put the jar in corresponding folder. For example, let's say your big project is involving all of these steps. You see this? Your big project is involving all of these steps, right? Now, and there is something called input data. Okay, input data is here. So you generally have input data in HDFS, or maybe it could be somewhere outside. All right. Now in the examples, you have these apps which are different kind of example. And now let's have a look at say pig. So you generally have a single workflow for this pig. And you could create another workflow here saying which involves all the applications you require and you can invoke the external applications. Okay, so say for example you can see the sub workflow here. All right, so you can see here this is a workflow which is calling other workflows. So here it's saying that action sub workflow, and this is the path of the place where we have kept our MapReduce workflow, and it's basically doing nothing but calling that particular workflow with this new configuration. All right, so you could create this kind of a complex project with all complex, uh, the dependencies. Now, in this case, let's take a look at the configuration of MapReduce. Okay, so we have got a folder called libraries in which the Java code which was there in SRC would be kept here. Okay, Java code will be kept here because MapReduce will be having the various kinds of information. Now, your workflow saying what all need to be done in this project will be defined in this format. Okay, now if there are multiple components, you could define all of those things here, that there is a pig script that need to be run, or you could create another project having multiple different kind of works. Okay, you can combine all of these apps into one by creating a big workflow.xml. All right. Now here you can see that there is something called job properties. Job properties is not something which we need in HDFS. This is something which we require while launching the program. Or if you are using the coordinator, in those cases you will have to define the job property in here. All right. Now, those who are not very comfortable in writing XML, they could use the visual editor like this one. Okay. All right. So you could create a workflow. You could create a workflow from the UI. All right. I think I'm little deviating, but that's okay. So either you could write the XML or you could create a workflow using this editor. You can see the editor. So let's say you are creating a Hive script action. So let's go back to our diagram, what we were trying to do. Let's say we had Flume, Scoop, Pig, Hive, and let's say this one is a MapReduce, and then we have another example. All right, so we first take Hive, bring it here. It says path to the script on HDFS. Okay, let me just browse it and go here and examples and apps and Hive. Okay, and this is my script. Okay, this is Hive site.xml, and we have to define a Hive site, as in you have to create a configuration with the Hive site. Okay, so yes, how do you create? Let me just think about, say, Hive site. Where is Hive site? Examples, apps, and let's say Hive. And here you generally have one site information as well. Okay, so we have done. And you could also define some more variables which are needed in case of this script. Okay, say every day you are running it today or tomorrow and so on. Now, parallel to Hive, you needed to run pig, right? You needed to run pig parallel to this Hive. So you can take up pig and drop this pig to your folder over there. Now, here in case of Hive, now let me go to one example of pig. Okay, so you have created a workflow which says that starting point is here, then there is a Hive, then there is a pig. Now maybe you have a MapReduce. MapReduce is basically combining cleaning data. Okay, MapReduce could be that, or what was your Java program maybe, or before this you have Hive, and I missed out on few things. Let's say SQOOP. Okay, so let's say SQOOP command is here doing something, I don't know what, but so where is the Flume? Do you see Flume anywhere? All right, all right. So SQOOP is there. Flume is anyway through the agent which is running in the backend. Backend, you don't need to define it here. Okay, you don't need to define it here because Flume will be pushing the data, right? Flume, you do not have to call. It's continuously creating the folder, right? So here, pig script is churning data from HDFS, cleaning it up, and then on the other side, you have SQOOP, which is bringing data through Hive. The Hive is cleaning that data, and then at the join, you will be having, maybe you have your own custom MapReduce job. Okay, MapReduce job, which is basically, say, here, I'm just providing few examples of where is my, okay, not jar name, we'll have go to lib, we go here. Okay, so we have these properties. Okay, we have to fill these properties. We'll have to fill these properties as in this is my input data, this is my output data, and so on. Okay, so so this is our MapReduce, and afterwards we might be running, say, our what was that? Java program. Okay, this Java program will basically call our Mahat, and that should be it. Okay, okay. We could define, say, whatever is our Java program's name. Java program's name is, say, Mahat main. That is our Java program, which will be calling Mahat. Now you can see this good graph which we have created. Starting, this is our starting point. On the left hand side, we imported data using SQOOP. Then we ran Hive, and once Hive, and on the right hand side we are running Pig. And when both of these things are done, we are doing something with MapReduce job by combining this data. And after that we are calling Mahat here. Okay. And once that is done, we will call another SQOOP program. We'll call another SQOOP program here, which will take the data back from here to somewhere, to the, okay, this SQOOP program, which is basically going to run and save the data into the web server. Sounds good to you, everybody? Now let's just save it. Let's just save it. Okay, now the page has been saved, so it will appear in your workflows. And using coordinator, now you can schedule this workflow. How do you fork and join? Did you notice that in case of, say, my workflow here, this is the old one. I should have kept different names. So Sushant's question is, what should be folder structure and for the code and script? This folder structure should be a good example, the one which we showed you. Okay, that should be a good example to start with. All right. Maven, so there are tools which generate the folder structure. I'm not sure if there's a Maven, what do you call, Maven project which is doing it. Okay, but this is a good recommended structure. Okay, the one which we showed you earlier. Now in this, the question which I had from Randhir, how do you fork and join? So you can see that I did something here. There is a fork here, right? Now let's say here again we want to do a fork at this point after MapReduce. We want to do a fork. Okay, how do we do that? Or after Java program finishes, we want to send recommendations to two places. One to one web server, other to other web server, right? Let's try to edit it. And where is that edit button? Yeah, here you can see. Now to, let's say you have another SQOOP command which takes the data where else. Okay, or you want to do some kind of another analytics using Spark or something, but let's just take a case of SQOOP. So using SQOOP, you can drop on the either the left panel here, this left drop-in point, or right drop-in point. Okay, if you drop on the above this between these two elements, that means it will be inserted in the sequence after and before. So here we are just dropping it on the left hand side. So you can see that we have created a parallel one. Okay, this one say copies to, say, OLAP, Okay, that's our name. Copy to web server. Copy recommendations to the web server. So you can see that we have successfully created, oh, why it's not taken, to web server. See that? Now, you can see that this is how you can generate your fog from the UI. Okay? So everything has 4 drop-in points. You see, everything has 4 drop-in points. And you can even drag and drop things from here. You hold from here and then you can drop anywhere. Okay? So this is a very easy way to edit the whole graph. Okay? So this was an example of OOZIE. Now once you are done with it, you could go to coordinator. Now there is a good question from Veena. Question is the fork and join just defining the flow, or does it also store output of one program and pass it to another? No. My answer is just defining the flow. Okay? The store is HDFS. Most of the communication between programs happen through HDFS or any other data store you have. All right? That was our, the workflow. You could create a coordinator job. You could create a coordinator job. Okay? The coordinator UI is again a little complex. You have to define the input data, output data. So which workflow to schedule? Let's just pick up our workflow. Why is doesn't Okay, so let's say we picked up the first workflow which we had, and how often do you want to do? You want to run this recommendation generation every day. Okay, so you could just save it, and every day at 00 this will run. Okay, and sometimes you want to define other different schedule. If you have an advanced syntax called cron job, you should know what does it mean by cron job. Okay, cron job is basically a way to define calendar. Okay, so once you know that, you can define your cron job. Good. So this was the way we could save and schedule our work, and this will keep on getting executed automatically at that period of time. Sounds good to you? All right, so that was the way from the UI. If you want to schedule from the command line, you can also do that easily, okay, by saying things like this. So if you want to schedule, let's say, this particular part, you could go to the terminal. Where is my terminal? I could go to the console, copy the login, copy the password, paste it here, that's it, and increase the font a bit. Now here we could run, okay, so it says that the configuration is not specified correctly. So do we have examples folder? No. Okay, So examples folder was, I think, in D or F. Anyway, let me just copy it again. So the way to do is these commands. All right. All right. All right. So I'll just copy my examples. And yeah. So here you can see there is an examples dot job properties, and we could run that using. So let's say we are trying to run this part. We could even added our this file and change the various arguments. So not this one. All right. So you can see here you can change the name node. In case of us, I think name node is now a dot something, not localhost, and job tracker is a dot cloudxlab.com, and here also it's a dot cloudxlab.com or h1.cloudxlab.com, either way. So this is job properties. When you are executing from command line, this job properties is required to discover the server from where to pick up the data, pick up the workflow, and everything. Everything else is inside the inside this place. So here we are saying my workflow application path is at this location, and output directory is this. Okay, so either you could execute things from the coordinator. The best practice is to run things via coordinator. Okay, not via the command line, because command line here you are only doing it once. There it's doing it periodically, and every time your workflow kicks in, it might kick in on any of the node in case of OOZIE. While when you are launching here manually, you are doing it on the local box. What if that local box is shut down? Therefore, OOZIE relies on yarn to execute even the workflow, because workflow has to be executed on some machine. Although MapReduce, Pig, Hive, all of those dependent component are basically distributed in itself. But if you're running things from the command line, it's not a better way to run it. Okay, to just give you an idea on how to run things, I am running it from here. Okay, so you could schedule the job like this. It has given us job ID. Now you can go and track what's happening with my job in the panel here. Okay, you could go to job browser and you will see what's happening to your job. Okay, so it says that it's doing something. Okay, this is I think this is yesterday's work. All right, so that was about it. All right, so that was our OOZIE, the discussion on OOZIE. There are many actions which we have already seen. If you go here to the job designer, okay, what was that job designer? Not here. You go to workflows, dashboard, editor, workflows. So if you pick up this, so there are all kinds of jobs which are available inside the OOZIE. Okay, there are all kinds of actions which are available. If you edit it, you can see there is Hive script, then Hive to server script, then there is a Pig, then there is Spark program you can write, then Java program, then SQOOP, then MapReduce job, Then there is a sub workflow, meaning if somebody has created another workflow, you can call it. And then there is shell. Shell means any command you want to execute. Then SSH, you want to execute on any specific host, a particular program if you want to execute on a specific host, because this one will run on any host at any point of time, because this workflow might run on any of the nodes. Now then we have HDFS file system. You want to do some sort of copying operation, deletion operation, or something like that, and then you want to send email. Like every program has to have email. Now you want to do some streaming, and this is something new. This is introduced in the new scheme of things. So looks like there is a script program which can be executed. Oh, this is Hadoop streaming. You remember about Hadoop streaming, the Python one? Using that, okay, you could write any script as our mapper and reducer. Okay, so if you want to do that, so yeah, you could define that here. But the strange part is it doesn't have. Okay, never mind. So if you want to do a DHCP operation, you can do from here. Or you want to say write a kill program to which everything will add. We could do that from here. Okay, kill is already, one is already there, kill, the default one, the stop. Okay, and yeah. So that was pretty much about SQOOP. Okay, all right. See that? Okay. Now submit this, schedule it, or what you want to do with it, that's up to you. Okay? You can share it with somebody and whatnot. Alright? Now that was about our job browsers. Yes, you can submit the job from here also. Schedule it or submit it. Okay? This arrow you see on the right top, that's for submit. Alright, so that was about OOZIE, and I hope we have not discussed Mahotia, or did we discuss Mahot yet? Alright, alright. So for Randhir, it is still showing the, Randhir, what is your email ID? Let me just have a look. Okay. Alright, so Randhir and Sridhar, I think I should be able to fix your problem by morning. Okay, let me check. I did not get time today, and everybody, because it's a weekend, so my team is having off, so that's the reason. Okay, by tomorrow I should be able to get it done. All right, so okay, so I'll just go through everybody's email ID and try if and give them the access for 20 days. Okay, not 20 days, maybe 25 days. Okay, by the end of this month. All right, good, good. All right, so let's take a break for 10 minutes and come back and discuss the rest of the things. Okay. In the remaining part, we'll discuss a couple of interesting things, which is comparing various solutions and comparing the and do the run recommender. Okay. So break for 10 minutes. Back by 10:10. Yes, Avina, let me have a look after the session. I sincerely apologize for Sushant, can you call at 11:30? Okay. All right. So should we start now? All right. So hi, I'm back. Should we start now? Great. Let's start. All right. So again, now the very important aspect of the whole Hadoop ecosystem is that it gives you enormous amount of ability to churn huge data and complex data. When I say complex data also means the kind of complex problem you are trying to solve. The variety, okay? The variety. So variety of the problems and variety of the, so some of the variety of the problems are fairly complex, and for those cases we need to do different kind of computing. Okay, and that's where Mahat comes into play. It's a machine learning library. It's a scalable machine learning library. So machine learning means ability to infer so we'll just talk about machine learning after this. Scalable means it can scale to bigger data sets. Okay, it's based on Mahat is based on Angie ETL's paper called MapReduce for Machine Learning on Multicore. Okay, it was started as a Lucene sub-project, became Apache top-level project, and then so became quite popular. But now, as of today, the state of Mahat is that it's being migrated and it's being recreated in Spark as well, on top of Spark as well. So Mahat, by definition, is a keeper or driver of the elephant. It's a Hindi word for in the Indian word for keeper or driver of the elephants. All right. So what exactly is machine learning? Machine learning is basically programming computers to optimize a performance using example data or past experience. Okay, so sounds very complex when you hear that based on the past experience program is learning. But if you look at what does it mean by learning, given the past data point, projecting future is one of the learning which we focus in machine learning. It's a branch. It's a branch of artificial intelligence for designing and development of algorithms. So if you have, so in very simple form, let's say in year 2012, somebody's salary was $200. Okay. In 2013, the salary was 300. 2014, salary was 400, and 2015, what will be the salary? Anybody? Yes? 500, right? Yes. So you intuitively said 500. But if we have to get this done programmatically, how will we do it? How will we do it? Okay? Or let's say, let's do a little twist in the same problem. Let's say this is 205, this is 298, 8 and this is 410. So what will be the salary in 2015? Now here the graph is not very linear and this is the real scenario. Okay, or let's put a little bit more twist to it. So this is what basically constitute as prediction. We are predicting data based on the past. This is your past experience. This is your past experience, and this is the prediction. This is what is we are calling it prediction. Okay. So how do you solve these kind of problems generally? What you do is you take x and y axis, plot this data. You say that, okay, this means 100, this means 200, this means 300, this means 400, and this means 500. Okay, and you say this means 11, 12, 13, and 14, and 15. Okay, so and this is say 100, 200, and so on. So for 200 we have 2012, and it's little greater than 200, little greater than 200. So I'm little moving it away. Now, in case of say you can see say 2013, our value is little lesser than. Yeah. Now in 2014, the data is around, let's say here. So this is the data which we are given. And so what you do is you do the curve fitting. You say, okay, let me just try to draw a line which goes through it. So either you could shift the line like this, or you try to see which one is fitting most. You see that? This is called linear regression, as in we are creating the best fitting curve, or we are creating the best fitting line. Okay, best fitting line through the data. How do we do the best fitting? We try all possible such lines. We try here, we try here, we try to rotate this line and then see which one is closest. Which one is closest? By closest means how much is this point away from the actual point? How much is this point away from the actual point on the line? So this way we compute the standard deviation and sum it up, sum these differences, this difference, this difference, this difference, and we try to minimize it. We try to minimize by trying all possible combination. Okay, so this technique is called linear regression. We keep on trying and trying again for a lot of values. Now when I say trying and trying again and again, you would be getting the feeling that it will be an intensive task, because if you think about the computation, you will be doing a computation for all one angle change in this line, and then for every angle you will also try different kind of paths. So for this you will try one, and then once you have done with this place, you will just try to move a little bit and then try a little bit more. Okay, so this is something which is called linear regression, and and this becomes more. First, you can see that even in two variables, this is fairly complex. Now, the moment you have more variables, as in the person who's in 2002 salary was 205, and this person's not this person. Let's say the the gold prices were say 100, or okay, gold, and then you have gold prices for various years. Okay, and you have gold prices for all kinds of Okay, so you have gold price. Now you have three things to plot. Now how do you plot three things? For every value of gold price or every year, we have to plot the salary, right? You'll have to have three-dimensional graph. Similarly, if you have more and more columns being added, there'll be more dimensions to it, which we may not be able to plot on usual graph. And that's where the problem starts becoming complex. So one complexity is, even with the two variable, you have to try so many slopes. You have to do a lot of hidden trials, right? And the other complexity is you might have more dimensions, as in more columns. And the next problem is that you may have too much data. There are so many points on this. So effectively, all of this combined, okay, when you have millions of record of all of this, it becomes a really complex problem to solve. There are too much of computation that is required, too much of data that is required to be handled. And that's where things become interesting. That's where things become interesting. On one hand, you have complexity. Other hand, you have volume and variety combined together. So that's where we require machine learning on Hadoop, and that's where we require Mahat. Okay, so once we have drawn this kind of predictive graph, then we can do all kind of computation, as in, for this we can simply say, okay, sorry, for 2015, if we have to find out 2015, we'll just take this line, extend it. How can I remove these? Okay, so I can extend it from here. It hits the curve at this point, and then we can go down. Okay, then we can go down like this. Now you can see that this is the point which computer has figured out. It will be 300 and 200, 300, and 400, maybe 500. So 1, 2. So I mean, I definitely made some mistakes here, and that's why it is looking like this. Okay, so ideally it should come somewhere here. All right. So basically, we can given this kind of we draw. Say we have to predict for 2015. We will draw a line from here to this, the line which we have predicted that this fits the points clearly, and then we can find out the point. So the idea I'm trying to say is, with a very small numbers, this is small data. Now, the concept is very simple. We have to find the line or the curve which is closest to these points. And once we have figured out that curve or the line which is fitting all the points, then we can start plotting the graph, start predicting the future values. Okay? This is called machine learning. This is called machine learning. Now, here we were happy that there was a linear correlation. Now, there could be, say, when we plot this data, we might reach to, how do you select? Okay. Okay, so there could be a scenario, say, let's say this is your graph, these are X and Y, this is your X, this is your Y, and you have all kinds of relationships, okay, like this. Now, there could be a relationship like this. We have so many data points. Now, to fit a graph into all of this is a complex thing. So given a value of Y, if we had to predict X, what will be that? Okay, so this could go complex really soon. So if we can figure out, okay, this is the curve that is fitting into this, that is really challenging task. Given all kind, like imagine this, there are all kind of points. Now tell me, for given this value, what will be the predicted value? It will be very difficult to predict that. So these are the complications, and that's where the whole idea about data science and machine learning begins. All right. So so based on the empirical data, we are just given the empirical data. We have to figure out, start predicting. Learning means predicting this graph, predicting this kind of a model that, okay, my data is fitting into this model, and based on this data model, we can start predicting the future. Okay, so that's about machine learning, and this was like most simple way I could describe things. And yeah, so was I able to convey what does it mean by machine learning, everybody? The graphs and these things were a little too complex. Okay, Randir is saying yes. All right. Veena, was I able to convey what does it mean by machine learning? Great, great. All right. So so looks like everybody got it. All right. Now, so the one which we just did is called supervised learning. We have a clear idea that these are our columns, these are the fields, and this is what we want to do. Okay, so this is called supervised learning. Okay, in the given data, we have, okay, for x the value of y is this much, for y, for another x the value of y is this much. That is called labeling. Labeling is very clear. For example, if we want to predict from the image what is the number written on there, we will convert image into a big number. We will create the image into, say, thousands of numbers, and then against thousands of numbers there will be thousands of columns, and there will be one additional column which will say that the output is this. Okay, so for one there will be image which will be represented by 1,000 columns. For two there will be images represented by thousands of columns, and so on. Okay, so we have a, so in this image recognition case, we have a clear idea that this is our input and this is our output. This is our input, this is our output, and that is called supervised learning. Supervised learning means using labeled training data. Labeling as in, given an image, we labeled it. That, okay, this image represents 0, this represents 1, this represents 2. That is labeling. Okay, and then creating classifier. Classifier means some kind of a model which does the prediction for us. Okay, classifier means, in case of most simple classifier we did was drawing that line through these points. That was classifier. Okay, so drawing that line through these points was one of the most simple classifiers. So we, using the labeled training data, using those data points, creating that line is called creating a classifier that can predict output for unseen inputs. We could extrapolate afterwards, right? So based on the input data, so the example which we took was actually for supervised learning. Now, unsupervised learning is, we have no labeling of the information. We don't have clear picture on what exactly is input. Okay, let's imagine this. You have got emails. You have got emails, and inside emails, you are given a task that, okay, I have this 1 million emails. I have 1 million emails. Just divide these 1 million emails into 5 buckets. 5 buckets. Okay. Now, how do we do it? Okay, so how do we do it? What is the criteria? What is the criteria of bucket? Okay, that is something you have to decide. You will decide something like a distance between two elements, meaning how two emails are, how differing those emails are. Maybe you will compute that based on the words frequency in the email, or maybe the URL, the kind of word frequencies you will try to compute in email, and then compare which emails are similar in nature. Okay, so that is called unsupervised learning. Unsupervised learning could be given all the news websites, connect same news together. That is unsupervised learning. Now, semi-supervised learning is somewhere between. For some data, you have some labeling. For some data, you don't have a labeling. So, for example, let's take I'll show you what does it mean by unsupervised learning in mathematical terms. So, let's say you were given this kind of data that okay, let's say on this axis you have not like this, I'll just type it. Okay, so size of apartment and price of apartment. Okay, so if you draw this, you gather all the statistics, you might have many points here. Okay, like this, and you might have this. Okay, you might have this kind of graph. Okay, now you are asked that can you just convert this into two groups. Okay, so you can just basically the objective is to bring this. Okay, you have to tell what is the center point and we have to tell how much spread it is. So basically this is called unsupervised learning. You are given this data that these are the points, this is the size of apartment and this is the price. For the same size, there is another apartment which is at the zero cost. So generally, when you do it, convert it into two unsupervised learning way, the chances are that this will be city and this will be village. Okay. So basically, this kind of classification is called unsupervised learning. All right, and something in between is called. There are many applications for machine learning, starting with. Okay, there are many applications for machine learning, starting with uh, all kinds of things, starting with speech, handwriting recognition, natural language processing, and all kind of things. I mean, wherever human finds it difficult to write an algorithm to do the prediction, the machine learning tool could be quite useful. All right. All right. So this is a very important slide. Okay. So there are many kinds of tools, and machine learning is not something new. Machine learning is basically a new form of the same thing. The problem with machine learning earlier was that machine learning needed a lot of data. Why? Because if you have more number of points, the chances are you will be able to draw a better graph. You will be able to draw a real inference. You will be able to draw the correct conclusions if you have bigger data. And if you have bigger data, then your learning will be better. For example, if you have like a couple of records, the chances are you will have a wrong conclusions. Okay, so if your data size is few lines, if your data size is like 3 records, you can do a machine learning. You can do the machine learning using whiteboard. Just the way when I started the topic, I asked you 4 records, and you were immediately able to predict. Okay, the salary of the person is 500. Right? If you have few lines of data, you can do the machine learning on the whiteboard. But if you and similarly you could draw on the whiteboard. So analysis as well as visualization you were able to do on the whiteboard. Now if your data size grows to kilobytes, kilobytes is in thousands of records, in those cases you cannot use the whiteboard. If for 1,000 records, I think I'm not capable enough to do that on the whiteboard. If I can at most go up to like maybe 50, 40 records on the whiteboard, but nothing beyond it, right? For that, you might have to, when you go into 1,000 to a million record, you will have to use tools like MATLAB, Octave, R, and for processing. Now, when the data grows to lower MBs or lower GBs, you will have different set of tools for analysis and visualization. Analysis and visualization. For analysis, you will use NumPy, SciPy, Weka, or something like BLAS or LAPACK. But for visualization, you will have to use these kind of charts. But when the data grows beyond GBs, the data goes say 10 GB, 20 GB, 30 GB, 100 GB, and so on, then this visualization of data is not possible because I mean human has its own problems of first, when you draw so much of data on the screen, you don't have that many pixels. Okay, even if you had that many pixels, your eye may not be that sharp to detect those changes. Therefore, there is no visualization tool when the data grows to gigabytes and beyond it goes to hundreds of gigabytes, and and there's only analysis tools. So if somebody asks me, then what about how do you visualize such data? So the general strategy is you either sample the data, or summarize the data and then present it in the graph instead of trying to present terabytes of data. Terabytes is huge. Terabytes is 10 to the power 12 zeros. Okay, 10 to the power 12 zeros. Those many records. 1,000 billion record is a terabyte, and it's beyond. If you try to draw it on a graph, it's almost difficult, right? And when the data grows to that size, that's where these tools like MLlib from Spark or Mahout are the solutions you're left with, or Spark are, because you will require a different set of tools. Why? Because this cannot be done using single computers. You cannot use a single computer to churn hundreds of gigabytes of data, that too with the complexity of machine learning, where there are so many CPU cycles that need to be required. Okay? Therefore, you will require multiple computers with multiple processors, with multiple cores to solve your problem. Okay, and that's where the domain of Mahout or Giraffe or MLlib or SparkR or GraphX comes into play. Now there was a question from Veena, is R used in big data different than regular R? Yes, there is a slight variation of R. Here there are two ways of using R. One is running R as Spark streaming. Okay, so either you could use your R program as a mapper, or you could use R program as a reducer. That is the most rudimentary way of using R in case of Hadoop. But that would not solve your problem, because the complex algorithms like compute the matrix multiplication of billion record against billion record is almost impossible to do using R on a normal computer, and even to do that using R on Hadoop streaming is almost impossible. And that's where Spark R comes into play. Spark R is far more closer to R than Hadoop streaming with R. Okay, And Spark R is very much similar to the normal R, but there are minor variations that you can, when you go through Spark R, you will understand that. All right. So you can see that there are many use cases of Mahat. So it starts with simple ideas like collaborative filtering, the one which we did just now. And what exactly is Mahat again? Mahat is a collection of library for machine learning, and there are four general general categories in which it provides you the library. It provides you these four different kind of libraries, four different kind of classes and functions. One is called collaborative filtering. So Mahat provides you this program which generates the recommendations for you. Second is clustering. Clustering as in, given my data, group it into four different classes, or given the the value, the details of all the cars of the world, given the details of all the cars of the world, prepare a hierarchy, meaning Ford A and Ford B are closer to each other as compared to Mercedes and Ford. So prepare that kind of hierarchy depicting the closeness of various models of car. That's kind of an example of clustering. Classification means learn from existing data and start predicting. Classification is something very important. And the fourth thing is frequent item set mining. So frequent item set mining means we basically take the existing history of our customers, and then whenever people are buying few items, we tell them, hey, generally people who buy these three items also buy fourth item, okay, or people who buy this also buy that. That is frequent items mining, okay. So while collaborative filtering is, this user bought this one and this you have bought this one, and therefore you are similar to that user, and therefore you may also like this product. So collaborative filtering say you may also like that, while frequent item set mining means people who bought these things also bought that. While in clustering means group your customers in two clusters, or group your customers on three clusters, and maybe you can use this criteria, okay. Given the purchase history of all the customers, bucket them in three, create three groups. That is clustering. Classification is given all your customers, create a hierarchy depicting how customers are related, how customers are closer to each other. Okay, so clustering and classification is actually quite I gave a wrong example for classification. Classification is something like a labeled thing, meaning we know that these people with this purchase history is of this age. People with this purchase history is of this age. People with this purchase history is of this age, that is, and predict what is the age of this customer given the purchase history. This is called classification. Okay, so these are the Mahat's use case. Now, we will just go through the collaborative filtering example. Collaborative filtering means you may also like this, okay? The recommendation, all right? So we'll just go through a recommendation example here. Okay, so what are we going to do? We are given the history of people, okay, in the form of, I'll show you. If I go to my file browser, okay, here we you go to data, here in the data, you have these movie lens data. Movie lens data gives you the information about the users. Shows that people with this ID, person 1 liked movie 1193 this much. Okay, this person gave to this movie 5 rating at this particular time. This time is in milliseconds since 1st January 1970. Okay, so given this data, you have to generate recommendation. Although Mahat gives you a straight away algorithm to do this, but the problem with this example is that you have to convert it comma separated first. Okay, you have to convert this rating.dat to comma separated. Anybody? So what we have to do is this has to be converted into, all of this data has to be converted into something like, first we have to remove this part, okay, and this also, and then we have to remove this, we have to replace this with a comma. Okay, so this is what we need out of this data. Okay, so we need to translate this data, and that's where I was telling you that you have to clean the data or reformat the data, because our Mahat expects the data to be user ID, comma product ID, comma rating. Here we are given user ID, movie ID, and the rating out of 0 to 5, and this one. Sometimes your rating might be from 0 to 10. You might have to convert it into 0 to 5. Okay, that's what Mahat expects. And then once we have this kind of data ready, we can just feed to Mahat, and Mahat will give the output to us. Okay, so here you can see this. So now question to all of you is, given Hugh's file, we have to replace this with comma. Now how will you do that? Anyone? How will you translate this into this? This into this. Okay, let me try. Anybody? Okay, let me try to be more creative. All right, so how will you do this kind of, all right? So how would you translate this data into this? Okay, Randir is saying using map. Brilliant. But do you think you could do with Big or Hive or some other tool? All right. So we can use Pig for this. We will load this and separate it by colon, and then save it separated by comma. Okay. It's as simple as that. All right. So for that, you could use a script like this. Okay. I've already done this. Okay. So what you'll do is you'll load the data and say that my data is separated by colon. We are not saying double colon. We are saying colon because this Pig storage only accepts single character. Okay. And therefore, we are using 0, 2, and 4 because $1 will be empty string. Okay, because our data is having double columns. So between the two columns, it will be empty string. And then we are saying for each, generate only first 3 values, ignore the fourth one, and store it into ratings.csv. If you run this, you will get a data I've already done it for you. Yeah. Okay. We've already done this. You can see that. All right. I used pig with this script and generated that. Okay. You could also do the same thing. So please try to do it by yourself. Okay. And that will give you a good confidence. All right. Now, once you are done with that, you don't need to do any of this. I'm just removing this. Anyway, we'll see to that later. All right, so this is the workflow. So first we downloaded data, unzipped it, uploaded to the server, then we deleted the previous things. Okay, and where did we store? All right, so here that's my home directory. Okay, so let me just try to delete. This is my previous data from the previous session. Okay, so now we have a CSV. So here is my ratings.csv folder in which we have stored the data from using pig, using this command you see here from here to here, and then we have deleted our older data. Now we are going to run Mahat. Okay, let's try to run Mahat. Okay, so first we have to tell where is our Java location, and then we have to run. Okay. Okay, so it's running Mahat. It will take a little bit of time. Okay, so it has started doing the processing, and you will realize that it takes around maybe 5 to 6 minutes to get it done, and it'll take a considerable amount of resources from the cluster. All right. So you can see on our if you go to Ambari, you'll be able to see this. Okay. So that's how we generate the recommendation. Here, please pay attention to what is it that we have done. We have said Mahat recommend item based. This is the this is the thing out of the four things. This is the thing which we are running right now. Recommend item based as in collaborative filtering. And which algorithm? There are many algorithms which we use for computing similarity between the people, and then giving the recommendation, and then we are giving the input file. This is the input file, and this is the output folder. In this folder we will get the results like this. So in the records there will be part this, and the result will look like this, where this person 6029 is the person ID, will like this particular movie this much. This is the kind of result you will get out of Hadoop. Yes, those are inbuilt algorithms. That's right, Veena. What is the output from Mahat? This is the output from Mahat, Randir. Okay, so you can see that this is the user ID, this is the product ID, and this is the rating. This is, you know what is this? This says that I think this is the suggested rating, that this person will like this product this much. This person will like this product this much. So this is what we have done. For this person, these are the recommendations, and against each recommended movie, it's also telling us how much you will like it. Okay? So Randhir's question is, where is the user ID defined that we want to query, or is it done for? It is done for all user IDs, and that is why you want to take this data to your website or web server, where whenever user is visiting your website, you can show for that user what are the recommendations, right? The we cannot do the recommendation computation in real time so easily. That is why we pre-compute. We run this Mahat every night and do this generation of recommendations for all our users. And when the user comes to our website, we will show them, okay, for you, these are the recommendations we have. Okay. All right. In case we want to do the prediction in real time as in a person is selecting the movies, then okay, I like this, I like this, I like that, I don't like this, and so on. And then immediately we are giving him the recommendation. That is online online machine learning. Okay. The question from Randhir is, what happens when the new user comes? Brilliant question. The question is, say there is a user who, for that user, we have no history, right? We have no history, and that's a very brilliant question. So let's say there is a user for which there is no history we have. If we have no history about the user, we cannot really generate the recommendation. Reason being, Mahat needs to compute that which user resembles in the behavior to which user, and then start giving the suggestions from each other, right? And when new user comes in, Mahat doesn't have any data about it, and effectively there'll be no recommendations to that user. And this is where the idea about top and movies comes into play. Okay, or we use other characteristics about persons, such as age, demography, the age, country, okay, and other information. So, for example, we have more information about our user. So, I will show you that information. And what is that information? So you can see that 50% maps and 50% reduces are finished. There are a lot of things that are done. Okay, Vina's question is, so let me just finish Randir's question. All right. All right. Now, here top end movies comes to play. Okay. So if you go into, where is my data? Data is in, yeah. You see, here you have these many ratings, and under the ratings.dat, there is movie.dat. Okay, movies.dat have the characteristics of, it has the characteristics of, this. Okay, you see, it is showing you the movie ID 1. The name of the movie is Toy Story. It was released in this year, and it has these it is an animation movie. It is for children's, and it is for comedy. Okay, and yeah, and it was released. So similarly, Jumanji was released in 1995. It's an adventure movie. It's for children's movie and fantasy movie. Okay, and so on. So similarly, then the third one is Grumpier Old Man. So these are the details about the movie. So we then try to figure out what kind of movies do a person of this age and this kind of geography like. Okay, so we can do those kind of predictions also. All right, so you can see that this user 1 is a female. Okay, and then I don't know what is this information, and there is the age of the person. I think this is the age of the person, and then what date the user has signed up. Okay, so those are the various details about the users. Okay, you can see the movie lens data. So based on this data also you could do the predictions. Now see, this question is, can we give suggestions based on his interest? Of course you can give the suggestions based on the interest. For that you don't require too much of machine learning. That can be easily done using Pig or Hive. Okay, good, good. Now question from Veena is, I was thinking that reduce only starts when map is 100%. So in some cases, all right. So in some cases, actually, the combiner starts before that, and reducer. Yeah, reducer generally, yes, starts. But here, what you are seeing here is actually overall progress, not only one map reduce. It's an overall progress. So it is done. I think it is done. All right. So now we are able to generate the movie recommendations. Good, good. Now we can go to the file browser. Here in the folder called Recos, you have part 00. This is what has been generated by Mahat, and you can see that this user ID's recommendation are these many. I think it has generated 10 records for each. Top 10 recommendation for each user. Okay, they generated top 10 recommendation for each user. Here there are, since there are too many decimal places, that's why it looks skewed. All right, so basically it is able to give you the great set of recommendations. All right, you can try by yourself the whole process. It will be useful to you. Now the question from Veena is, what is the flow after Mahat? After Mahat, you could put this data into a web server, and or this data in email. So once you have generated this, maybe you want to send the email to all the users saying, hey, you will also like to watch these movies. Okay, or you could display it on the web server saying, okay, these are the movies you may also like to watch. Good. So that was our Mahat. We were able to successfully use log likelihood. You could try other algorithms. Okay. All right. So that was pretty much about Mahat. Let's move ahead. So try to import data from MySQL and back. You should do this. Build the OOZIE job for the fourth problem where we had two map reduces, and prepare the movie recommendation for yourself using Mahat with the data of group lens. Okay, for yourself as in you rate the movies you like and put it in CSV, add one more users to the total list of users yourself, and then see what movies it gives you as recommendation. Okay, so that could be a very good interesting thing you could try. So in this file which we have here, coming back here, so in this file called CSV, what was the rating.csv? Okay, okay, and in this rating.csv you add your own ID. that for your own user ID, and then put all the movies you like. Okay. You can also try to load this data in, Excel sheet about movies. You can load this data about movies in Excel sheet, and then give the ratings to each movie. The movies file I showed you here. Okay, so here in this there was something called. So here you could see these. In this you could import this into Excel sheet. It's not big deal because it's hardly. Okay, you can import this into your Excel sheet, give the ratings for yourself, put those ratings at the end of the file by a new user ID into that CSV, and see what kind of ratings you get, what kind of movie recommendations you get. Okay, so that's an exercise you can try. Okay, that will give you a good amount of exposure. All right, so you should try that. This is a very important. Actually, I'm going to try this. All right, I haven't, although I had planned to do it, but I have not done it. I'll try this. So, or you can download fresh data from MovieLens and try the recommendation again. Okay, so that will be your movie recommendation done by yourself. Is this problem statement clear to everyone? So in that CSV file, add yourself a new user, and then give the ratings to all the movies, put your ratings in that CSV file at the end of it, and then try to see what kind of recommendations Mahat gives for you. And those top 20 movies you should go and watch. All right. So that was an overview of OOZIE and Mahat. We can now go ahead with the other parts. All right, we have two things to do. Three things to do. One, we will do a quick comparison of Spark and Storm, and then we'll go for NoSQL comparisons, and then we'll go for project description. All right. All right. All right. So we had earlier discussed that how Spark could be used to process streams of data in real time. Okay. So there is another solution called Apache Storm. It's basically a distributed real-time computational system similar to Spark streaming. And the features of Storm are it can reliably process unbounded stream of data, as in the streams of data which don't have a beginning or the end. It can be used with any language, and it has been clocked at around 1 million tuples per second per computer. And then it's scalable, fault tolerant, as in case one node goes down, another node is available. Scalable, as in there are more and more nodes can be added at any point of time, and guarantees that the data will be processed. Okay, even though a set of data could be processed again. Okay, integrates with the queuing and database technologies because the data will be coming through the queues or through the database. So it integrates with those kind of technologies and able to give you the same results as Spark streaming is. So Storm was the de facto solution before Spark streaming came into play. So Storm is basically for real-time analytics, continuous computation, distributed RPC, as in Continuous computation as in we are doing the computation continuously. There is no beginning or the end. Or distributed RPC, meaning if you want to call a remote process from thousands of computers parallelly, you can utilize Storm for that. And you can do online machine learning as in real time. If you have built a model already and when the data is coming in, you can launch those algorithms in real time and do the ETL, of course. Now there are many companies who are using, because Storm has been around for quite a while. So here's a quick overview of a quick comparison against Spark Streaming. Storm does record at a time, while in case of Spark, there is always mini batches. In case of Storm, the latency is sub-second, less than a second, while in case of Spark Streaming, the latency could be a few seconds. All right. In case of Storm, every record is guaranteed to be processed at least once, while in case of Spark, one record will be only processed only once. Okay, that's a compromise Storm has to make in order to guarantee that every record is processed at least once. Now, with respect to implementation and API, Storm was created at backtype when the Twitter was backtype. Before the Twitter, it was backtype, and while Spark was created at UC Berkeley, Storm was Closure, implemented in Closure. Spark was in Scala. Storm was in Java. It provides Java API, while Spark provides Java, Scala, and now Python also. And Storm does not have a batch framework integration, while Spark has a batch framework integration, such as normal Spark. Okay, so Spark Streaming has a batch framework integration. Now, with respect to production support, in case of Spark Streaming, you have Databricks, and that is the big difference actually. And resource manager integration is something that will impact you. So the three things that will impact you, the reason why would you like to go to Storm against going to Spark Streaming? One, if you want to process one record at a time. Okay, if you want to do strictly record-wise computation, if you don't want mini batches, then you go for Storm. Second, now in case you are okay with mini batches, okay, and you don't have Hadoop right now, but you have mesos, then you go for Storm. Otherwise, in all other cases, you go with Spark Streaming. Okay, if you have already Yarn, there's no need of, you cannot run mesos parallelly. So that's an important aspect of deciding between Storm and Spark. All right, you can have further details about these. Now, these are common questions which I keep facing from all the students, which is regarding NoSQLs, which one to use where. This is a very subjective discussion. So I will try to be little more, little more, what do you say? I'll try to be little rash, okay, when describing these databases. So I mean, so that we can quickly understand the overall classification of the databases. So first one is Redis. Redis is basically an in-memory database. In-memory database having a disk support, as in case the computer shuts down, you do not lose data. All right. So, but Redis is limited by the memory of the machines, and it is it is very useful for rapidly changing data. When you have really fast changing data, then you go for Redis. And when your database is of size that can fit into the memory, okay. And the examples are to store real-time stock prices, leaderboards, analytics, and communication. And wherever you used Memcached before, there you can use the Redis. All right, MongoDB. MongoDB is a document-oriented database. Document-oriented database, if you need dynamic queries, if you have preferred indexes, not MapReduce functions, if you need good performance on a big DB. If you wanted CouchDB, but your data changes too much, filling up the disks. So for most of the things that you would do with MySQL or Postgres, but your predefined columns are holding you back. If you don't want so many columns and so many relational structure, instead you have this complex structure of JSON, then you will go with MongoDB. All right, Cassandra is useful to store huge data set of similar behavior like SQL. Okay, Cassandra is a good database. It provides you a SQL kind of language. So if you do not have a Hadoop stack, Cassandra is probably the go-to database for most of the big data needs. And so when you need to store huge data that doesn't fit on one server, but you still want a friendly, familiar interface like SQL, then you go with Cassandra. For example, the examples of Cassandra could be web analytics, to count hits by hour, by browser, by IP, etc. Transaction logging, as in you want to keep track of logs of various transactional systems. Now, the data collection from huge sensor array, meaning IoT. If you have thousands of sensors, you have placed thousands of sensors on devices or on the ground, and these all sensors are sending you the data per second. Okay, so you will get thousands of records per second, and you want to keep track of all of this. Okay, in those cases, Cassandra could be quite useful to you. Now, there is another database which we have already discussed, which is called HBase, for billions of rows and millions of columns. Okay, as simple as that. Hadoop is still the best way to run MapReduce job on huge data sets, but if you use, it is best if you use Hadoop SDFS stack already, because HBase would require you to install the Hadoop stack. HBase doesn't work outside Hadoop stack. So the only downside of HBase here is that first, HBase doesn't provide a great query language. Second downside of HBase is that you have to install the Hadoop ecosystem completely. Okay. So the same thing, if you need a lot of data and you don't want to store on you don't have Hadoop ecosystem, you can go with Cassandra. All right, so it can be used for search engines, analyzing log data, any place where scanning huge two-dimensional joinless tables are the requirement, you go with HBase. Similar to HBase, you have Accumulo and Hypertable. All right, you can have a look at more of these details at this blog, which is quite useful. All right, that's pretty much with respect to the comparisons of NoSQL and the comparisons of Storm and Spark. All right, now I have a project discussion. All right, so the project is pretty simple. The objective of this project is to do the sentiment analysis of a movie called Iron Man. So I have all the things downloaded already into the Cloud Labs, and you can use all of this data. All right, we will provide you the access to all of this data, no worries, and your logins will start working maybe by morning. Okay, morning as in after around 12 hours from now. So the objective of the exercise is to do the sentiment analysis based on tweets data downloaded from Twitter. The steps below outline a primitive strategy for sentiment analysis of the movie called Iron Man using Hive. It is up to you whether you choose to exactly do the same thing as mentioned below, or you could choose another strategy altogether. Let's just go through what are we talking about here. Okay, so you have to first log in into Hue. The URL is this. Okay, the URL for the Hue is this, and you can log in using your own login password. If you have the old one, you can use that one also. And you can locate the data. So the data required for this has been uploaded here. Okay, so the data is in the data folder. There is a dictionary, there is a time zone map, as in the relationship between time zone and the country name. And then there is a tweets. So dictionary shows you that this dictionary shows to you the sentiment of each word. Okay, sentiment of each word. And first we will break down the tweets into the one word and then join the word against the dictionary, and then we will also join each individual tweet's time zone against the time zone map and figure out the country of each tweet. So these are the three things which we are going to do, and based on that we are going to based on that we are going to do the analysis of sentiment. Okay, you can have a detailed look at this query. Okay, you can have a detailed look at this query, but before doing anything you should create your own database. Okay, and then you just go through the query, understand it, and run the query one step at a time. It will the end result of this query is to, let me change this. Okay, let me change this, and d.cloudxlab.com. All right, so I think this will be right. Okay, one more thing, I need to make changes. All right, so you can see hive ddl.sql. That's what we are talking about. Okay. All right, so go through this query and you will understand what's going on. Try to understand this. Also, this JSON survey is available in the same folder as Hive. Okay, and go through that. Once you have got this table in place, then you will have to install the Hortonworks driver. Go through the way how to install the driver. Once that is done, in the configuration mentioned below, this one, okay, so I will say, yeah, here in this configuration diagram, so you have to mention here, instead of Hadoop 1.nobigrator, you have to mention c.cloudxlab. The port is 10,000. Okay, the port is 10,000. Login password, you will have your own login password. Okay. And then the access the refined sentiment data with Excel. Okay, so I'll show you. So once we have created this, installed this driver, we'll be able to connect to Hive server. Hive server is running at 10,000 port, and then you can start creating the sentiment, representing the data here. Okay, I have outlined the overall steps. You can go through these overall steps and try to represent it. All right. And you will have to share your Excel sheet with me along with the database you create. Okay, that will be pretty much about the project. All right. In case you are looking for real-time project, do let us know. Do let us know. And I mean, you'll get an email called "Stay in touch." Okay. So stay in touch. You will get an email, and then we can have the other, you know, if there's a real-time futuristic project which is coming in, you can be made a part of it. All right. Okay. And so that was pretty much about the project. You can do the variations of these approach. Either you could use some other technology such as Hive, or you can completely use a different algorithm, such as maybe use a natural language processing, or you could even do the various kinds of deviations from this approach by downloading the Flume data by yourself or setting up your own pipeline of the data. Okay, you could create your own program to download data from the Twitter. Okay, you could also use other ways of representing data. So Vina's question is real-time project only for, not really, not really. You don't travel anywhere, so you can work on the project from anywhere. All right. So we tell our customers. Now, question from Randhir is how to download data from Twitter. That's a good question. Let me show you. Here, if you go to sentiment files folder, you will find Flume folder there inside sentiment files. Now, inside this Flume, there is this configuration. The FlumeConf, if you remember FlumeConf, which we discussed, this is that configuration file. So you can run a Twitter agent from the command line by providing this configuration file. And you will have to update with your consumer key. You'll have to generate this consumer key by signing up with Twitter and get the API key with them. Okay, so that's what you got to do. All right, so that's pretty much about the project. And Sridhar is saying, can you email this document? Do I need to send email? Because, okay, are you not able to access this document from the Google Docs? Sridhar? All right, I've just sent you the link. You can try that out. Okay. All right, so that's pretty much, and I hope I have been able to add some value to your learning. And please feel free to send me a LinkedIn request. Okay, so that's a good way to stay connected, and also follow our Facebook page, No Big Data's Facebook page, and that way we can stay connected. All right. All right. I'm not sure if, okay. I think these guys have started stopping the, add as a friend kind of a link. Okay. So try sending me a LinkedIn request and stay connected. The class ended does not mean that the relationship has ended. Okay. So our model is different. Our model is a little different in the sense that we are running the real-time projects right now with Dell and few more smaller companies, whereby we have different kind of opportunities, and we are trying to do the work which other people are not yet updated with. Okay, so for example, with Dell, we are doing Kafka-based real-time learning, real-time machine learning, which the other people they could not get it done by themselves. All right, so we are doing those kind of. Yes. If you face any problems with the project, you can contact me. Just write an email to support@NoBigData or Hadoop@NoBigData. Both are the same email ID, and I get a copy of every conversation. Okay. So stay connected, and that's pretty much about. Okay. All right. Thank you, Veena. I'm really happy that you find it informative and interesting. And all right, so I really enjoyed this particular session, although this is stretched beyond what I had expected ever. Okay, this is I mean, it has gone to how many classes now? I think we have gone to 12 plus 1, 2. Yes, so 14 classes. So, which is great actually. I found the questions from this particular session really great, and I thoroughly enjoyed the session. All right. Okay. Thank you, Randhir. Thank you for the compliments. I stay connected. All I have to say. Thank you, Sridhar, and I'm really happy that these sessions were helpful for you. Okay. So feel free to write our feedback on the Facebook, and yeah, stay connected, Sushant. Sushant, yes. Okay. All right. Great. Great. Yes. So feel free to drop me an email. Just that I may not be available on the phone because I may be in the middle of some session or in the middle of meeting, but I'll make sure that I respond to your questions. Okay. And yeah. All right. So you will get the certificate as soon as you finish the work. So here you will see that the project submission date. This is wrong. It has to be updated. We'll update it to the correct date. Okay. So project submission is generally 1 week from today. That is 7 plus December 12th. Okay. December 12th. And after that 1 week, you will have the project submission date. All right. So that's pretty much about it. Okay. So you will see your CloudX Lab details soon, as well as these dates will be updated. Okay. All right. Thank you very much and have a great day. Veena, upload the recording to your YouTube, or maybe put it in Dropbox and share it with me. Okay. Share it with uh, Sandeep at No Big Data. Okay, or maybe. All right. So yes, yes, Sushant. Yeah. Now we can have a call. All right. So thank you very much, and it was a great session. Stay connected. Bye bye. Have a good day.